Welcome back to the Python tutorial series for climate mathematics theory and applications. In this video, we will continue to cover Chapter 2, Basics in Python Programming. Some topics we will cover in this video include contour maps, symbolic calculations, and some various vector and matrices computations. Let's begin. In the last video, we covered plotting with Python. We covered how to plot the sine x wave as seen in line 14. We also learned how to plot an xy data based on a formula as seen in line 15, plotting this simple quadratic. We also saw in the last video how to plot a 3D surface using the line space method along with mesh grid and axis with projection equal to 3D. Today, we will be covering contour plots, and then we will go into plotting a 3D contour plot. Our setup is quite similar to the examples described above. X and Y we are going to set equal to a uniformly distributed set of points. We have 30 sets of points in between -1 and 1. We go ahead and utilize the mesh grid function in the NumPy package, and we are going to also define z as our function defined in the above examples on the xy coordinate axis. Now comes the creation of our contour map. We are going to access the matplot library method contourf with input variables x, y, and z, grabbing those from the coordinate plane from the mesh grid function. This 20 right here represents the number of levels that we would like to see in our contour map. CMap is the colored map that we are going to be using. This, in our example, is going to be the blue, white, red color scheme. You can find other color schemes on the internet. If you go ahead and Google Python color schemes for CMap, you will get quite a few listed color schemes that you can use. Next, we will be adding a color bar for our color map, which is the simple function of plt.colorbar open parentheses. Lastly, we are going to wrap our whole block of code with a plt show to get our contour map to actually show up, and this is what we get. Just a reminder on how to look at contour maps. We have the highest density concentrated right in the middle with this 0.9 level. Then as we slowly get outside of the center towards the edges, we are going to reach a blue which has a density of -0.9. Next, we will be plotting a 3D contour plot. This example kind of meshes together our examples that we have done in previous. So we are going to be creating our xy variables. Each of these variables has 100 points between the values of -1 and 1. We go ahead and define our function f in order to get values for z. We need to use that mesh grid function in order to create a coordinate plane of x and y points. Then finally rendering z using the function on the xy grid that we created. Now we will go into creating the 3D plot itself. We do need to set up the figure first. Then we will use projection equal to 3D on the axes method in order to notify Python that we are plotting in 3D. Then we are going to actually plot the surface using the plot_surface method with our values x, y, and z, with our CMAP Variate, which is a purple, green, yellow color scheme, and we have an edge color none. These two parameters, R stride and C stride, these are just defaulted parameters. They can be included or cannot be included. You do want to look at the documentation of the plot surface function if you want to change those default parameters. Lastly, before we plot, we're going to be labeling the plot. We're going to use set title to set our title as contour surface. We are going to set x label as the variable x, set our y variable as the variable y, set the z variable as variable z. And lastly, our view_init method is going to allow us to project our picture based off of the parameter given. This parameter tells us that we are going to be viewing our contour surface from a 30-degree angle. Lastly, we just wrap our whole block of code with a plt.show in order for this beautiful contour surface to actually appear. Now, let's begin our symbolic calculations with Python. First, we are going to start off with defining x and y as symbols used for derivatives. To make x and y symbols, we are just simply going to use some variable assignment with x equal to the symbols of x and y equal to the symbols of y. After this definition of x and y, we can use these two variables as symbols for derivatives and integrals, and basically as placeholders for symbolic calculations. The diff command, seen in the highlighted text, is going to take the derivative of x squared with respect to x, outputting the correct derivative of 2x. Now, we're going to be creating the function of x squared rather than manually inputting it in as seen in the highlighted text. We are going to define f of x as the function of x squared. Now we are going to be defining the result is equal to the differentiation of f of x with respect to x. Then wrapping our result with a print statement explaining what the result meant, we get a final output line of the derivative of the function f of x with respect to x is 2x. Now we are going to be creating the function of x squared times sine of x. Just a little reminder, we are accessing the SciPy module in order to use the sine trigonomic function. We are then going to be saving the result as the differentiation of f of x with respect to x. Just a little reminder, we do have a product of two functions, so when the Python language uses this diff function, they do internally do the product rule for derivatives. Wrapping our result in a print statement, we get the output. The derivative of the function with respect to x is x squared times cosine x plus 2x times sine x. Now we will move on to creating a multivariate function, namely x squared plus y squared, seen and defined as fxy. We are going to be defining result x as the differentiation of our function xy with respect to x. we're going to define result y as the differentiation of f of xy with respects to y. Wrapping both of those results in appropriate print statements, we do get the partial derivative of the function with respects to x is 2x, and the partial derivative of the function with respects to y is 2y. Next, we will be going into integral computations. We are going to integrate x squared from 0 to 1. We are accessing the SciPy module in order to use the integrate method. Your first parameter for the integrate method is going to be a function, namely, in our case, x squared. The second parameter of the integrate method needs to be a tuple that includes first the variable that you are integrating with respects to, followed by your lower bound, followed by your upper bound. In our case, we are taking the integral with respects to x with a lower bound of 0 and an upper bound of 1. We do get an output variable of 1/3. In line 24, we are going to integrate cosine x from 0 to pi over 2. Using that SciPy module with the integrate function, we are going to access a cosine function also found in the SciPy module. We are going to integrate with respects to x on the bound 0 to pi divided by 2. Just a reminder, we do have to access our variable pi in one of the modules that contains it. Math, SciPy, NumPy all have the variable pi saved in. We do get an output variable of 1.0, meaning that the area under the curve of cosine x between 0 and pi over 2 is exactly 1 unit. This concludes part 2 of chapter 2, Basics of Python Programming. In the next video, we will continue to cover chapter 2 and dive deep into vector and matrices computations. Thank you.